Hello everyone. In today's lecture, we are going to design a synchronous mod-n counters. In the previous lectures, we have discussed about synchronous up counters, synchronous up-down counters using JK flip-flops and T flip-flop. In today's lecture, we are going to discuss about mod-n counters. So synchronous counters, 3-bit synchronous counter or 4-bit synchronous counter. If it is a 3-bit synchronous counter, it can count from 0 to 2 power 3 minus 1. That is 0 to 7. Altogether, 2 power 3 values can be counted. If it is a 4-bit counter, whether it is up counter or down counter or up down counter, if it is a 4-bit counter, then it can measure values from 0 to 15. Altogether 2 power 4, 16 values can be counted. Suppose, for example, if I need to count a value in between. For example, if I need to count till 5, 0 to 5, and then it has to go back to 0. I do not want to count till 7. If I want to count till 6 and then if I want to go back to 0, that is up counting up to 6 and then again I have to down count. I do not want to reach till 7. Similarly, the case with 4 variables also, 4 bits also. Under such circumstance, under such situations, how will we design the counter? So mod n counters, or if I want to count a value which is not in 2 powers, then to design counters of that kind is known as mod n counters. And again, we have the applications almost similar in all the cases of counter. Wherever we require counters, we can use this too. And here the design procedure again is the same. Here the required number of flip-flops and the type of flip-flop will be chosen. Draw the excitation table for the flip-flop. Draw the state diagram. Draw the excitation table for the logic diagram. Draw the K-map and find the minimal Boolean expression. Draw the logic diagram for the up counter. Now we are going to design a synchronous mod 10 counter. If you see here, mod 10 is not a power of 2. Right? So see, we have a mod 8 counter, that is mod 7 counter, 0 to 7 to count, as well as we have mod 15 counter, that is 2 power 4. We do not have a mod 10 counter. So it's a number which is a non 2 power number. So how to design this? So first let us consider the type of flip-flop and then the number of flip-flops required. The number of flip-flops can be only in 2 power. So if we consider 2 power 3, then it can count up to 0 to 7 wherein the number 10 exceeds that. So 2 power 3 cannot be used. Suppose if I use 4 flip-flops, then 2 power 4, it is 14, that is 0 to 15. So 10 comes less than that. And so that can be used. So a 4-bit counter can be used. Draw the excitation table for the flip-flop. That is the second step. Here we are going to use a T flip-flop and this is the excitation table for the T flip-flop. This is a state diagram. If you see the state diagram, it is counting, totally it is counting 10 levels or 10 states. It is counting from 0 to 9. Right, and then it goes back again to 0. This is what is mod 10 counter. Now we have to draw the excitation table for the logic diagram. Already we have the excitation table for the T flip-flop and we have discussed how to fill this excitation table in the previous synchronous up counters and up down counters. So this is the present state and this is the Q dash or Q star is the next state. And from the present state, this we have filled it from the state diagram. From the present state and the next state, we will be calculating the value of t, that is the inputs. So once after calculating the inputs, we have to find the minimal Boolean expression using K-map. So we'll be using K-map So here K-map was drawn. It has been grouped and equations are framed. So we have to implement these equations. T3 is equal to Q3 Q naught plus Q2 Q1 Q naught. So T naught is equal to 1. Here T naught 1, logic 1 is being given directly. Then if you see T1, it is a complemented version of Q3 and Q naught. So see, where is Q3? Here we have Q3. From Q3, we will be taking it to Q3 dash. So here we have Q3 dash, right? So from Q3 dash, it is being taken to the ZAN gate. Along with Q naught is also given, and that forms the input to T1. Similarly, T2, Q1, Q naught. Here we have Q1, and here we have Q naught, right? It is being given to an AND gate, and then it goes as input to T2. Similarly, for the third case also. This is how we'll be designing a mod n bit counters in general. This is for your assessment. Thank you. I hope you have understood the sessions on flip-flops.